more about string processing and some of the input-output stuff, and also kind of continue the conversation about pointers, although at the moment we'll be kind of restricting our attention to doing it with strings, because a string's name basically is its own pointer. And what that means is that the syntax of how you would pass a string to a function makes you think that you're passing the string, but what you're really doing is passing a pointer to it, because you can't pass an entire string, or yeah, basically, because it's too big. Okay, so let's and then we'll also talk more about the stdio, more about what was I going to say? Oh, ASCII and how strings are encoded. All right, so let's just get a function going, and let's just define a string. So car my string of is, oops. Okay, something, silly like that, okay? Now, if I specify a number inside the brackets, then I am specifying the size of that string as an array of characters. If I don't, then the fact that I've got an initialized value here as hello world, how many characters does that take up, hello world? So 5 for hello, 6 for the comma, 7 for the space, 12 including the word world, 13 for the exclamation point, and then there has to be one more byte for a null terminator to say this is the end of the string. Okay, so that would take 14 bytes to store. And so if I had put a 14 here, that would fit, obviously, okay? If I leave it blank, then what the compiler will do is just sort of calculate it for us by looking at the string that I'm using, and then, I don't have to count. Okay, but the key is that we have to remember that there's really a 14th character that's put at the end of the string, namely the null terminator, okay? And the reason we need to do that is otherwise we don't know where the end of the string is. If I just hand you a string and I don't tell you anything about it, well, okay, and so let me actually back up. I can't just hand you a string. What I can hand you is where the string starts in memory, right? I can say, it starts over here, but I don't have, there's only two ways for you to know that you've hit the end of it. Either there's a special character that designates that, or I would have to tell you in advance how long it is, okay? Which maybe I know, okay, but maybe I don't know the length of the string in advance, okay? Like with this string, with hello world, yeah, I know how long it is. I can count, right? We're not morons, okay? But what about if we accept user input and we say, okay, user, you can type at most 32 characters or something, just make up a number. Do you know that the user's gonna give you back all 32 characters worth of stuff? Maybe, maybe not. Maybe they only give you 5 characters worth, okay? And it would be inefficient to process all 32 characters as if something had happened if they only gave you 5 or whatever, right? Now, 5 versus 32 may not seem like a huge deal, but what about if you were dealing with like text processing for like the entire works of Shakespeare or something? That's just a massive pile. You don't want to be processing data unnecessarily, okay? Now, strings can also have other special characters, okay? And we've already seen one of these with the \n. Okay, so the \n is what on a like what does that do in terms of the terminal? Yeah. Yeah, new line character. Okay. Um, and which is I overheard. How many of you guys are in the internet programming class with Dr. McCartney this semester? So I happened to overhear. Well, I guess this was Tuesday. Yeah, because you guys meet Tuesday, Thursday, right? You guys talking about terminal and ASCII encoding, right? And there's the difference between a line feed and a carriage return, and also like there's not a consistency between different operating systems as to how a line is ended. In some operating systems it's just the line end, and others it's a line end and a carriage return. And yeah, so all of that same stuff is kind of what's going on here. Okay, but the new line, the \n, that encodes in ASCII as a line feed. Okay, um, and actually, I should have maybe poked my head in the other day when I heard him talking about that. Did he mention what really is the difference between a line feed and a carriage return? Like, why do we even have those two terms? And carriage, what the heck is a carriage? How many of you guys have used a typewriter? Mr. Worley, are you the only person in the room who's ever used a typewriter? None of you have ever used a typewriter. Have you seen a video of somebody using a typewriter? Okay, what happens if you type a whole bunch of stuff and you get right? Okay, that's a carriage return. Okay, but that's not a line feed, that's a separate process, right? Of you advancing the paper one thing. And often there's also a ding, right? To tell you that you've hit, 40 characters or something from the beginning, and that it's time for a carriage return. Now, you can disregard that and keep typing. Eventually, you'll be not on the paper, right? But the bell, the carriage return, the line feed, right? All of those things are really typewriter uh, ideas. Okay. Now you might say, well, then why the hell do we have those involved with a computer? Well, guess how computers, the earlier ones, used to print through a teletype, which is essentially a computer-controlled typewriter, right? So there literally would be a carriage, there would be bells, and it would, do this. I mean, so have you ever seen teletype machines? Yeah, I mean, look them up on YouTube, right? And in fact, there's somebody. I'll find the video and send it to you guys because it's kind of hilarious. That he hacked together an old teletype terminal, thing, to be his Linux terminal. So when he types something in and hits enter and it, spits out stuff, it's an actual typewriter like doing it, and so it's slow as crap and whatnot. But it's kind of hilarious, right? Okay. Huh? What? For teletype? Yeah. Yeah. So pretty cool, right? Okay. So yeah, ASCII is sort of riddled, if you will, with a lot of these sort of old concepts, but then with them, we've gotten repurposed for computer use. Okay. And so some of the analogies of like a physical carriage that you're sliding back to the left don't make sense unless you've used a typewriter before. Okay. And, you know, when people were doing computing in the 70s and 80s and heck, even 90s, like I remember using a typewriter when I was a kid. I mean, I wasn't writing essays for school on it, but I was, you know, doing stuff with it. So, yeah. Um, and this actually, just an interesting bit of trivia. Why is the keyboard laid out the way it is? Why is the Q in the top left? Yeah, why do we use QWERTY layout? Yeah, okay, but it's actually less efficient than other layouts. Okay, so QWERTY was designed to be deliberately inefficient. Huh? People type too fast. Well, what's wrong with typing too fast? If you're using a typewriter, there's a problem. Okay, because how do typewriters, especially the old ones, there'd be those levers, right, that would bam, 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 right? So what happened? So the original typewriters, way back in the day, were just laid out in alphabetical order, right? I mean, what other order would you put it in? Okay, and what happened is typists got so fast that the keys, what happens if two of those things come up simultaneously? It starts to jam, right? So the QWERTY layout was designed to minimize the probability of a jam of the little arms. Okay, well, now we have computers. Do we have to worry about jams of arms? But everybody had already learned QWERTY, so why make another standard? And so we just are stuck with it. Okay. There is actually a second English layout called Dvorak. And what Dvorak does is it moves all the keys around to maximize the alternation of left hand, right hand. Okay, because if you think about it, if your left hand is doing something, your right hand can be moving into position for the next thing. And if you can alternate that and maximize that, then you can type faster. Okay, but it's a different keyboard layout, and that means you have to unlearn QWERTY and relearn Dvorak, and good luck with that, right? So I tried at one point and said, nope, forget this. Yeah, exactly, right, and that's it's muscle memory. I don't have to think to type, right? Because I've been doing it for so long. I just, I find the H and the F and the J key because those are the ones that have the little thing on it, and then off I go, right? So yeah. Anyway, okay. But on the subject of Ascii, okay, let's actually pull up an Ascii table, um, and um, look at the encoding for the strings, okay? And okay, so here, let me blow this up a little bit so it's a little easier for you guys to see. Okay, so this very beginning one, the null character, is hexadecimal 0. Okay, so as a byte, it would be just a byte of 8 zeros. Okay, so that one we're obviously going to use, and that's how we know that we've hit the end of a string. You remember when I said the bell? There it is. That's its ASCII encoding. Okay, and so if oops, uh, that's not what I meant to do. Went down too far. Okay, so the first 32 things in ASCII are all, damn it, it's because I zoomed in. I'm sorry, guys. Damn it, Bobby. Uh-huh. Uh, the first 32 things here in ASCII are all um, non-printable things, okay? And so from 0 to 31, those are non-printable characters. They don't have a symbol associated with them, but they're important. Okay, so a lot of these are, in addition to the bell, the carriage return, the line feed, that sort of stuff, you've also got things that are used in communications between computers, like, hey, I'm about to send a message, okay, I'm ready to receive it, or okay, I got it, or I acknowledge your thing. Did you guys talk about like um, ack and knack and stuff like that with in the internet class? No, maybe you haven't yet, but okay. So you got characters that you can use to kind of encode those things, and then we get into mostly the symbols required to do the English language, right? So you've got some of your punctuation and special characters there, your parentheses, your times, your plus, right? Basically the shift key, shift of the top row of keys. then you've got your digits, you've got colon and semicolon, less than, equal, greater than, question mark, ampersand, and then starting at hex encoding 4-1, you've got capital A, and then, well, you know the order of the English alphabet. So 26 letters later, right, we get down here, and we've got the bracket, the backslash, the caret, the underscore, the other kind of left quote. So that's the thing that's under the tilde key. And then all the lowercase English letters, okay? And then you've got curly braces and the tilde and delete, okay? And there's all 128 of them, okay? So the other thing I overheard him say is talking about the difference between ASCII and extended ASCII. Yeah. Okay. So ASCII originally was a 7-bit encoding scheme. And so that allows you to encode only 128 different patterns. And you just looked at all 128 of them. Okay. Most of them are taken up by stuff to represent English language and symbols and stuff that we use often in programming, you know, brackets, curly braces, that sort of thing. Okay. So great. That's fine. But it's very American centric, right? And that's fine. We invented all this stuff, or pretty much. So, Merca, right? But then there's also extended ASCII, which sometimes I slip and just consider it to be part of ASCII, which adds an 8th bit, and that gets you therefore another 128 characters. Okay, most of what's in the upper 128 characters, so from 128 to 255, not all of them, but most of them are other Latin alphabet characters, or there's a couple of Greek symbols in there. Okay, so for example, the pi symbol is in there. That makes sense, right? Because, well, that's an important mathematical constant. Um, and then it's also got, for example, all of the Latin characters like in Spanish, there's in with the tilde over it, right? That makes the y sound. Yeah. Or in French, there's C with the little dangly bit under it that tells you it's a soft C versus a hard C. It's called a cedilla. So a bunch of those symbols are there, and then there's their lower and uppercase variants. Okay, that's not surprising. Um, so all of that stuff is there, and that's great. For our purposes, we'll just ignore all of their existence and only worry about strings and stuff that include the regular original 7-bit ASCII scheme, which is the first 128 characters. Okay, and I mean, there's no. I mean, if we can figure things out for the first 128, the rest of it's okay. Yeah, just add some more stuff. Okay. Now that said, then what's sort of the problem still, even if you use 256 ASCII characters? I mean, that's a lot of characters. Okay, but it's a lot of characters for Latin alphabet languages. Okay, so anything that uses the Latin alphabet, you're fine with. Okay, but what about if you're Greek? Well, you could say that's pretty close to Latin, right? I mean, a lot of the letters line up, not perfectly, but yeah. But you know, let's pick on Zhongquan here, right? What is he gonna do? Yeah, you're SOL, right? And the reason, of course, is how many characters are there in the Chinese language? It's thousands upon thousands, right? Whatever, I don't know what the exact number is. Okay. Um, but there are many, 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 many symbols because the language is built around character ideograms rather than an alphabet. Okay, fine. But what that means then, of course, is that you have an encoding problem because you need the ability to encode thousands of different things. Okay, and that's just Chinese, right? What about if you also want to do, say, Korean and Japanese? and Cyrillic, which is the Russian and other Slavic languages use. Or I find myself in this situation quite often. What about if you need to be able to type uh, ancient Babylonian, cuneiform? Hmm? I was being somewhat sarcastic. Okay. Um, yeah. Well, actually, it's not a chisel that you would use. So the cuneiform, uh, wedge shaped, would you'd use wet clay, so soft clay, and you have this sort of wedged shaped instrument that you'd press in, and then you would bake the clay to harden it. So you wouldn't actually be chiseling anything. Okay. Um, and the clay pieces tended to be about the size of one's hand. They fit comfortably in your hand, so you'd hold it with your left hand and do the wedge stuff with your right. Um, so, yeah, I am somewhat joking when I say I have this problem often of needing to be able to type cuneiform or even Chinese. Actually, I don't speak Chinese, but um, there are some very interesting documents or artifacts, mathematical artifacts from ancient Mesopotamia or ancient China that I like to use in teaching. So, for example, have you ever read the Nine Chapters? Or yeah, right. There's some really cool stuff in there. So this is an ancient, Chinese mathematical text, and there's a lot of really, really neat math that goes on in there that you can look at it and from a Western standpoint, you could be like, oh, yeah, they're doing, I can think of it this way. But it's a completely different way of thinking about certain problems. And one of the things I love about them, some of these problems, is if you try and solve it with Western algebra and stuff, it turns into just a train wreck of algebra. But if you solve it in this other kind of way of thinking, it's so much more elegant. You get the same solutions ultimately, but it's a different way of thinking. So anyway, and in the cuneiform, there's an ancient tablet. Let me actually show you guys a picture of it, just because hashtag liberal arts college. Um, there it is. So you might call this one of the world's first spreadsheet. So there are a bunch of numbers written along here. The stuff along this top row is stuff written in like words, okay, that explains basically what the column headers or what the columns contain. And then the different columns are numbers written in cuneiform sexagesimal, so base 60. And this has to do with sort of ancient geometry. It's sort of related to kind of a Pythagorean theorem sort of thing, although the details are quite complicated. Yeah, so this is all numbers, and if so when I found myself teaching this stuff, well, I wanted to be able to typeset cuneiform in LaTeX because that'd be cool, right? So there you do. So in order to do that, by the way, you can't use Ascii, right? Ascii just doesn't have enough room, and so the other newer scheme is called Unicode, which you guys maybe have seen. Python is pretty Unicode compliant, and so you can put Unicode characters in Python and it just works. Um, but the downside is that you're spending like 32 bits to encode any letter, right? Because 32 bits allows you to encode like 4 billion things, roughly 4 point something billion. That's a lot of things, right? There's a lot of characters in Chinese, but it's nowhere near billions, right? So if we take Chinese and Korean and Japanese and linear A and linear B and Egyptian hieroglyphics and all of the emojis that you guys use every day, and we throw all that together, we're getting nowhere close to 4 billion, right? So, um, yeah. And I'm a little salty that, by the way, so you guys know how there's all these emojis and periodically new emojis come out, right? So we have a Unicode character for the poop emoji, but they rejected a proposal to add Klingon to Unicode in the 1990s. And I find this just outright ridiculous. Yeah. So anyway, okay. So that, by the way, like I said, it would fit comfortably in the size in the palm of your hand. No. Well, if I'm very careful and I remind myself of because like I said, the stuff in this top row I cannot read because I don't know Akkadian. Everything in the bottom from there down is numbers, and so yeah, it'd take me a minute to remind myself, but yeah, I can read the numbers. Um, it's all in sexagesimal too. There's a little bit of damage, you've got a couple of cracks here and scuffs. But and not to toot the horn, but I said this fits comfortably in the palm of your hand. How do I know that? Because I've held it in the palm of my hand. It's in the rare book room at Columbia. It was really neat to get to see it. So anyway, um, all right. So let's go back to this. Sorry for the digression. So this is stored right in Ascii, and I think last time at some point we looked at a memory dump to see, okay, there it is in memory, this character, this character, this character, this character, and so on, okay? Um, and so what are the kinds of things that we might want to do with strings, okay, in order to like process them? Well, what kind of stuff did you do in Python when you were doing strings, dealing with strings? Huh? Yeah. Wouldn't being able to know what the length of the string is, if you don't already know that in advance, wouldn't that be a useful idea? Okay. And there is a built-in function to do this. Okay. It's called the string length function, not shockingly. And that is included, and this is why I had to include string.h because it's part of that uh, collection of functions. Okay. So for example, I could say um, printf, and I could do something like the string and then %s, %i, and then I need to pass this what? Well, what string do I want to print? My string. And what's the length of it? It's the string length of my string, okay? So nothing particularly exotic there. And so let's just return 0 to the operating system. And let's switch directories. And GCC it. And execute it. Oh, sorry. Let me remove that break and put the line break here, just for cleanliness. Okay, 13 characters, is that correct? Yeah. Okay, but is it what's missing in that count? The null terminator. Okay, and that's fine, right? If we define length as being everything up to the null terminator, but not including the null terminator. So what this means, though, is that you have to be cognizant of the fact that even though there's only 13 characters, the string still does take 14 bytes of data space to encode, right? Because you've still got to have the null terminator. We just don't count that as part of the length of the string because if I wanted to, for example, iterate over every character in the string, I wouldn't want to mess with the null terminator, right? I'll just leave it alone. But I could mess with this string, right? So in addition to computing the length, right, what are other things that I might want to do to that string? I haven't actually changed the string by computing its length, but I could also change the string by doing stuff to it. What kinds of things might be good idea to do or useful to do for whatever reason. Okay, make it all capitals or equivalently all lowercase, right? So do one of those two things. Um, huh? Concatenation would be useful, right? If we had multiple strings and we wanted to shove them together into some new big string, okay? Um, and with concatenation, we would really have three strings, the two inputs and then the new one that's going to have all of their collective stuff put in, okay? But let's take the making everything uppercase or making everything lowercase. Okay, they work, the idea is essentially the same thing. And so let's actually write a function to do that, okay? To take a given string and make it all uppercase or lowercase. And for that, to kind of crack the code as to how to do that, let's go back and look at our Ascii table for a second, okay? So what I want to do is let's look at the lowercase part of it, okay? A through Z, and they're all in order, fortunately. And what's the hex encoding for little a? 6-1. Okay, it's not 61, it's 6-1, right? So this 6-1, right, this is hexadecimal, so just be clear on that. Okay, and B is 6-2 and so on. That's quite logical that they'd go in order from there. But 6-1 is an important number. Okay, that's where the lower cases start. And if we go up to the upper cases, where do they start? 4-1. Okay, so what's the difference between the lowercase starting point and the uppercase starting point? In hexadecimal, it's 2-0, right? 4-1 to 6-1 is 2-0 is the difference. In sorry, as in base 10, what is that? 2-0 hex is 32, right? Okay, and that makes sense. It's got to be at least 26 because there's 26 letters. Okay, and then you guys remember there were between the uppers and the lowers, there was like the bracket and the slash and stuff to pad it out so that it would be 32 off. Okay, so if I am given a character that's lowercase, I can make it uppercase by subtracting 2-0 from its value. Okay, and similarly, if I wanted to make an uppercase lowercase, I would add 2-0 hex to its value. Okay, does that make sense? Okay, except I don't want to. Do I want to do this for every single character in the Ascii table? No. What do I want to change? Just the letters. Okay, so where are the lowercase letters? Well, we said that they started with, what was it, 4-1 or 6-1, excuse me? Starts with 6-1, but where's the Z? 7A. Okay, so if I want to uppercaseify everything, I want to subtract 2-0 from their hex encodings, but I only want to do that to the symbols that are between 4-1 and 7A hex. Okay, if I did it for other things, then I would jumble up all my characters and it would be unreadable. Okay, because maybe I would turn like a letter into an exclamation mark or something. Okay. That actually might be useful if you were writing like a simple encryption thing, like a message scrambler or something. But for our purposes, we don't want to do that. Okay, so, all right, so what did we say between 4-1 and 7A? Okay, good. All right, so let's write a function that's going to do this. So we'll call this function, well, let's see. It's going to return nothing, actually. So we'll just make it a void. And we'll call this uppercaseify. And what am I going to pass this thing? I want to pass it a string. Okay. Now, I can't pass it a string. What I can pass it is a pointer to a string. Now, the way C is defined, I can do this. Okay, and say, all right, there's going to be some sort of input string coming in, okay, and when I type this, what does this make you think that I'm giving this function? Doesn't it look like I'm actually passing the string to it? Yeah? Because it looks like I'm passing just any variable, some number or whatever. But what that really is a pointer to it, okay? There's a second way I could have written, instead of car input string, with the brackets, that's equivalent and maybe technically more correct. I'll talk about that later. For now, let's just use this slightly sloppy notation. Okay, good? Okay, so what should this thing do? Well, I need to have a loop, right? And my loop needs to go through every character in this string. Yeah? All right, so how might I set up my loop here? There's a couple ways I could do it. How might I think about setting this up if I was using a for loop? Well, a for loop's got to start with something. Okay, so what do we want to call our counting variable? Huh? Count. Okay, great. What should count's initial value be? Okay, because the arrays and strings are all zero indexed. Okay, and then what's the maximum value that count can ever be? Or what's the max value it should be? Okay, for our particular string, 13, but does this function know how big the string is that's going to be handed to it? No. Okay, so that means we either need to define our for loop in terms of the string length, or we need to do it, think of it more as a while loop and keep going through it until we hit the null terminator, right? One of the two. Yeah? For the sake of demonstration, let me do the latter, because iterating with the string length and known in advance is pretty easy. Okay, so we'll do the following. Okay, so we'll say while input string of, okay, I need to have an int count equals 0, and I'll do this while that character is not equal to, oops, what? What is the null terminator? In Ascii, yeah. Yeah, okay, so there's a couple ways I can type this, and probably the easiest way is \0 inside a single quote, not a double quote, okay? That defines a character. And the reason that I'm doing the character notation here is because what I'm looking at, if I look at one character in a string, I'm looking at a character, not a string, right? And so if I'm doing something with the string, what I'm really doing is just character by character. Okay, so while I'm not at the null terminator, I want to keep doing some stuff. Okay, so this function that we're writing will have no idea what the string length is, and for that matter, it won't care what the string length is. Okay, all right, so what do I want to do as I scan through the string? And let's say that nope, I haven't hit the null terminator yet, no problem. Okay, well, what do I want to do? How do I turn a lowercase letter into an uppercase letter? I subtract 32 decimal or 20 hex. Okay, but do I want to do this for any ASCII character? No, I only want to do it for the lowercase letters. Okay, so that means I need to have a condition. Okay, so what condition? All right, Well, the letter that I'm looking for needs to be between what and what? Yeah, okay, so the current character needs to be greater than or equal to 0x61. That's the lowercase a. Okay. And it needs to be greater than, or sorry, less than or equal to, what? What was the lowercase z? Wasn't it 7f, was it? Yeah? Well, let's just double check. 7a. Okay. So first off, let's make sure that the syntax of everything that I typed makes sense. So what is input string of count? That's the character I'm currently on, right? And I want to make sure that that thing is what? Between little a and little z. Okay, so little a, its hex encoding is 0x61. And if you want to type a number in hex, that's all you have to do, by the way. It's just 0x blah. Okay, and so how do I know it was going to be 6, 1, and 7a? Well, because we looked it up on our Ascii table. Okay. Um, I'm going to let you guys in on a little secret, but oh, and I need a close parenthesis right here. Okay. All right. So why do I have the double ampersand in there? That's the logical and. Okay. So inside each of the, well, they're highlighted yellow here. You see there's two yellow pairs of parentheses. One is basically saying, am I at least a little a? And the other one is, am I at most a cap or a lowercase z? And I want to be between them. So both conditions need to be true. So that's logical and the way you type that in C is a double ampersand. Okay. In Python, how would you have done that? Just the word and, right? That's one reason that Python is so nice. If I needed or, logical or instead of logical and, what would I have typed? Two vertical bars, okay? But I didn't need that in this case. Okay, so are we good with the condition? And in this case, there's going to be no else. Because what do I do if the character is not one of those letters? Just leave it alone and move on to the next one. Okay, so what that means is I'll put my iteration, well, count needs to increase by 1, and I'll put that outside the if condition because I still need to keep going through the string even if I've not hit a lowercase letter. Okay. All right. So if I do have a lowercase letter, what do I need to change the lowercase letter? How do I change it? So I need to redefine what input string of count is to be what it was minus. I need to subtract 20 from its encoding. Okay, and that's just because the lowercase letter started at 6-1, the upper one's at 4-1. Was there any reason why they put the upper cases first and then the lower cases? Could they have done it in the other order? Didn't matter. Somebody had to pick an order. They picked one, and now we're stuck with it. Okay. All right. So we're just going to take away 20 from it, and then increment the counter, move on to the next thing, and that's it. Okay, good. All right. So now let's test this. Okay, and let's say So let's run, what was my function called? Uppercaseify, and I'm going to pass it my string. Okay. So that's going to do the processing. And then, now notice I'm not returning anything here. Okay, and the reason is because I'm not actually passing the string to the function, I'm passing the pointer to it to the function. So the function is editing the string in memory, period, not a copy of it. Okay, and so now let's print the new string. And there we go. Okay, so we're ready to give this a try. All right, so let's recompile it and hope I didn't screw anything up. Good. Look good? Yeah? All right. So let me demonstrate one other thing here. Okay, and to make this easier to see, I'm going to go over into a full-blown, full-size console. Okay, I'm going to recompile this with the debug and the static flag so that I can use my debugger. Oh, sorry, I forgot one thing real quick, which is I need to figure out where the I want to know where the string is in memory just so that I can show you guys that. All right, so let me add that back in and recompile. Okay, and so let's just run it again real quick, right? So still works, right? But now I know where the thing is located in memory so that we can go look at that piece of memory. Okay, so now let's do the GDB. All right, so I'm going to put a breakpoint at main. I'm going to run, and then I'm going to start stepping through the execution of this. And I'm sorry, I haven't fixed the stuff. Okay, so that's about to run. Okay, the string hello world has 13 characters, and it's located at 0x7ffff blah 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 blah. Okay, so let's go out and look into memory, starting at what was it? 7ffff f 5f's EF80. Okay, so what do we see at that location in memory? What was the capital H in Ascii? Okay, so if you've got a computer in front of you, pull open your Ascii table, right? 48. All right, so H E L L O space or comma space capital or W O R L D exclamation mark null terminator. Okay. All right. So there it is. It's just an ASCII. No big deal. And it was at memory address starting at 7FFFFEF80. Okay. And that's just where it ended up. Fine. Okay. So no big deal there. And I am about to run the command to uppercaseify it. Okay, so what I'm passing to, well, let me just say this. Let me step one more time. Okay, so I just called the function to uppercaseify it. Okay, and what I needed to do is I needed to give that function the location of the string, okay, which was, where was it? 7FFF blah, 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 EFA0, whatever. Okay, so what I have just done here is I have dumped the contents of the registers. Okay, so this is something that we'll talk about a lot more because that's sort of more assembly level stuff, okay? But the reason that you cannot pass a string by value is because to pass anything by value, you have to pass it through a register. Well, a string are not guaranteed to fit in registers. Registers are 64-bit things, and the processor, each core of the processor anyway, has 32 of them. Well, and a few extras, okay? And they are called X0 through X30. And you might say, wait a minute, that's only 31. Where's the 32nd? It's this special one called the stack pointer. There's also the program counter, the CPU status register, the floating point status register, and the floating point something register. I don't remember what the C stands for. Huh? Yeah. Okay, but some special status registers. Okay, so what in order to pass a pointer to a function, I have to put the memory address. So the value I give it is not the pointer, or sorry, not the string itself, but its pointer. Okay, and the convention in Linux on ARM is that you start passing parameters in the very first register, X0. And lo and behold, what's an X0 right before I executed the command to uppercaseify something? That pointer, right? 7FFFEFA0, the value that's sitting in register 0, is exactly the pointer to the string, right? That's what I had to hand to the function for this to do anything, right? Is I gave it a pointer. I said, the string that I want you to go mess with is over here. Okay, me here, string over here. No? I don't know. I kind of, I just realized that I was doing Cartman, but with a little bit of Big AL thrown in. Did you guys know? Yeah, you weren't going to say anything. All right, whatever. You guys are pathetic, huh? No idea I watch South Park. Okay, so, all right. Okay, so now when I step through this thing, it's going to be stepping through I've gone into my function, right? So here when I define int count equals 0, I'm inside the uppercaseify function, right? And if I hit step, it's going to go through each line of that. Now, that will take a while because it's going to go through that loop over and over again, and I don't want to sit here while it does all of that. Okay, so let me go up to here, and let's look at our line numbers, and let me put a breakpoint at line 26, okay, so that it will keep going and do all of the processing, but just hold on the printing, okay? So I'm going to put a breakpoint at line 26. Okay, I'm going to type continue, and what that will do is keep running until it hits the next breakpoint. Okay, so it is about to print the uppercaseified string. The processing of the string is completed. I just fast forwarded through all of that basically. And what I want to do is look at what's in memory now at that location. Okay, so remember the string was located at starting at blah 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 EFA0, right? What's And we saw what it looked like before. What does it look like now? Well, look at the ASCII table. Yeah, all the letters are now their capital versions. But some of the characters have not been changed. So, for example, 2C was the comma. Well, I didn't want to change the comma, did I? Nope. 20 was the space. Didn't want to change that, so I didn't. Okay, but all the letters have been changed, but none of the other guys have been changed. Yes? Okay, so that's good, right? And we knew this was going to happen because it printed it correctly and everything was fine. Okay, but what I want to stress here is, have I changed, like, how many strings are currently in memory? Just one. So when I took in the string, or when I defined hello world, okay, I defined it having some uppercase and some lowercase, okay, and I uppercase defined it, and now it's all uppercase. Where was the original string I started with at this point? It's gone, right? I have overwritten that piece of memory. Okay, so what would happen if I wanted to, for example, do two things, uppercaseify it and lowercaseify it? I should probably make a copy of it, okay, before I do so, right? So the point is, the way we structured this, we have changed the original string, not a copy of it. And so we have destroyed information, namely what the string was before we started, okay? If I wanted to preserve that information for some reason, then I would have needed to make a copy and have my function change the copy instead of the original. Could have done that. It's not the end of the world, right? But I would have needed to do that. Okay, does that make sense? Okay, so if we can uppercaseify, can we lowercaseify? Yeah, okay, what's really the difference? Yeah, if so, let's go back to our code. What would we have to change to make this a lowercaseify instead of an uppercaseify? Because there's only two things. Yeah, okay, so the two things we would need to change is this would be add 20 instead of subtract 20, and then also instead of 6-1 and 7a, it would have been 4-1 and 5a, right? Those are the only two changes we would have need to make to do lowercaseify. Okay? All right, does that kind of make sense? Yeah? All right, so what would be a good assignment to do based on this? Hmm? Oh, give me a string, give me a character, count how many are in there. That'd be good. Yeah, something like that. Okay. Well, fortunately, you have that one. What would be another good assignment for, let's say, assignment 5 to be? Huh? The name. Gee, I couldn't imagine where you got that idea from, Patrick. Yeah. So, no, I have a better idea. Okay. Which is, how many of you guys have ever heard of the Caesarean cipher? You've never heard of it? Oh, it's easy. Okay. Um, you shift the letters. Okay. So it doesn't mean that you cut open and get the baby out of the womb instead of the other way. Um, but yeah, so Caesar had a cipher. Okay. And all you did is he rotated through the alphabet by 13 letters. Okay. So A would be, if I only rotated by one letter, A would become B, Z would become A, B would become C, C would become D, and so on. Okay? So if I took a message and I wanted to scramble it to make it difficult to read, I could do that, right? Yeah? Okay, and I could maybe also choose the number that I'm going to shift by. Okay, Caesar originally did this with the shift amount of 13. Okay. And so what that means is the first 13 letters you add to them, the second 13 letters you subtract from them because it's kind of a big circle. Okay. Um, and then what was the reason, or what's the utility of using 13 as the shifting amount? Well, how many letters are there in the English alphabet? 26. Okay, so what this means is how do you decode a message? With the exact same method that you encode it, right? Because what's shifting by 13? If that's the scrambled version and you shift it by 13 again, what do you get? Your original thing, because 26 letters is exactly how many characters there are, right? So the scheme for decoding and encoding is identical. Believe it or not, this was the procedure with the German Enigma also. The encoding and decoding worked the same way. The same machine did both. It's just that the letters shifted with a much more complicated pattern. And in what made Enigma so brilliant and also so hard to crack is if you hit the A key and let's say it shifts to become F. Okay, great. What happens if you hit the A key again? Something different than F, right? So there, the shifting rotated every time you typed a character, and there were little rotors on the machine that went through, and you had to have the rotors set into the correct initial positions and also the correct rotors in the machine, because it would fit for 3 to 5, depending on if it was the Army, the Wehrmacht, the Kriegsmarine, or the Luftwaffe version. Okay, and there were more rings than would fit in the machine, so you'd have to put the right ones in the right order, and then you could use the thing to decode a message that somebody else had encoded with it. This is just diabolically brilliant. And heck, we could do an entire class on encryption. That'd be kind of fun, right? Yeah. Well, so the thing that makes that difficult though is that to properly do encryption, guess what you need to understand? A lot of math. So sorry. Okay. All right. So I'll post a new fun and exciting assignment to become assignment 5, and yeah, which is really 6 because I count starting with 0. Well, how many times does this class meet in the semester, excluding the final exam? 28. 14 weeks, 2 times a week. So how many assignments basically are you going to have? Now, I say basically, it won't be exactly 28 because I'm not going to make you guys have something due the day of the midterm. That'd be kind of a totalfratmove.com. Okay. But yeah. So, yeah. Anyway. Huh? We'll talk about that in a few weeks. Yeah. So, all right. I will see you guys. We'll quit a little bit early. I will see you guys on Tuesday, if not sooner. And like I said before we started class, since I got my COVID booster yesterday and I feel like a bus has run over me, I may go home a little early today. And so don't expect to find me around today. Just email me. Okay, bye.